Hello students, let us now discuss in this video about PI, PD and PID controllers. Okay, let us discuss about PI, PD and PID controllers, which is proportional integral, proportional differential and proportional integral differential controllers. Okay, so let us go with proportional integral controller. Let us discuss about the proportional integral controller. So let me write the block diagram for proportional integral controller, which will have both proportional and integral part in the block diagram. So E of t is the input which is given to the proportional part Kp, and integral part which is the integration of, which would be the integration of dt, ki into integration of dt. Let me write that because ki is the proportional constant which is integral constant, and the output is n of t. Okay, so the equation for n of t would be equal to, so let me write the equation for n of t, so which is n of t would be the summation of these two different controllers that we have, which is connected to a single summation point. Okay, so therefore E of t gets multiplied with both of these blocks, E of t into Kp and E of t into Ki integral of dt. So that is what n of t equals Kp into E of t added with, because both are positive here, so therefore added with Ki into integration of E of t dt. Okay, Ki into integration of E of t dt. So therefore you take the Laplace of this equation, which is n of s equals Kp into E of s added with Ki into E of s by s. Because of the integral we divide it by s. Now you take E of s common in the left hand side. Okay, take E of s common in the left hand side, you will be getting Kp plus Ki by s, Kp plus Ki by s. Fine, so that is E of s equals Kp plus Ki by s. Therefore n of s by E of s would be equal to Kp plus Ki by s. So these are the two blocks which we add for the proportional integral controller. Okay, so these are the two gains which we added for proportional integral controller. So let us do that now. Let us write the block diagram for the proportional integral controller in terms of a second order system connection. What we do, so we have a summation where you take two different blocks for a controller. One is the Kp and the other one is Ki by s. The other one is Ki by s, and you give that to a common summing point. You give that to a common summing point where both will be positive. Okay, both will be positive. Take the output from the summing point, which will be given to the second order system, omega n square by s into which is s square plus 2 zeta omega ns, and take the output as C of s and take the negative feedback from the output. Okay, so now that is the negative feedback where R of s is the input, negative feedback you take, which is minus there. So therefore now we will try to write the equation for G of s for this particular proportional integral controller. Okay, we will try to write the equation for this proportional integral controller G of s. Now if you see that Kp and Ki by s, which is connected, is in series with the forward path gain of the second order system, therefore C of s by R of s can be defined. Before that we will see G of s here, where G of s equals Kp plus Ki by s multiplied by the second order system omega n square divided by s square plus, so s into s plus 2 zeta omega n s, 2 zeta omega n, because s is taken common. So if you multiply this equation with the omega n square by s into s plus 2 zeta omega n, by taking LCM, you see that it is kp into s plus ki divided by s omega n square divided by, I'll just multiply s into that denominator of omega n square divided by whatever we have, s square into s plus 2 zeta omega n s. So if you multiply the complete thing, you get s cube plus 2 zeta omega n s square, 2 zeta omega n s square. Okay, so therefore this is the equation of g of s. Now if you take the transfer function c of s by r of s, if you take the transfer function c of s by r of s, that would be equal to g of s divided by, which is kps plus ki into omega n square divided by s cube plus 2 zeta omega n square, which is whole thing divided by 1 plus kps plus ki into omega n square divided by s cube plus 2 zeta omega n square. Okay, now you take the LCM and cancel the denominator terms both at the top and bottom, so you get c of s by r of s to be equal to kps plus ki into omega n square divided by s cube plus 2 zeta omega n square s square plus kp omega n square s. Okay, so I'll just multiply it in the next step. So what do I get here is, which is equal to where c of s by r of s, if I multiply that kps plus ki with omega n square, I would be getting c of s by r of s would be equal to kps plus ki into omega n square divided by s cube plus 2 zeta omega n s square plus kp into omega n square into s plus ki into omega n square. So this is the total transfer function for the proportional integral control system, where ki omega n square you have, which will be multiplied by omega n square. Therefore, as natural frequency increases, therefore the time specification gets decreased. Therefore, the system response will be faster enough. Okay, as ki is increased, so ki into omega n square will also increase. Therefore, you can see the time specification gets decreased. Therefore, the system response will be faster. But here you should observe one more thing. S cube is there. See the order of the system, which is S cube, where the one pole is introduced into the system because of using this proportional integral. Therefore, the stability of the system is reduced. Okay, due to one pole introduction or one pole increment in the equation, you see that the stability of the system is reduced. So this would be the disadvantage of proportional integral. Now we go for proportional differential controller. We'll go for proportional differential controller. What is proportional differential controller? We'll see the block diagram of the proportional differential controller. Okay, so we'll see the block diagram of that, where E of t is the input, where proportional differential will have a proportional gain or the proportional block connected in parallel with the differential block, which is kd into d by dt, kd into d by dt, which is a differential block. These both are given to one summing point. Okay, these both are given to one summing point, and the output of that is been taken as n of t. So therefore, now we write the equation for n of t. We write the equation for n of t, which is equal to E of t into kp. We know that kp into E of t plus kd into differentiation of E of t, d by dt of E of t. Okay, Now what we do, we'll take the Laplace transform of this n of t, which is n of s equals kp into e of s plus kd into s into e of s. Because of the differentiation, it multiplied by s. Okay. So therefore, you take e of s common and take the transfer function, which will be, e of s take common, which will be giving you kp plus kds. Therefore, the transfer function, which would be the gain of this proportional differential controller, n of s by e of s would be equal to kp plus kds. So this would be the gain that you use for the block that you connect for a second order system, in the second order system. So let us write the block diagram of the second order system with this controller now. You have a summing point. You will be connecting to two different blocks. One is the gain of the proportional controller, which is kp. The other one is the gain of the differential controller, which is kds, which is connected to a summing point. Both are positive. Okay, connected in parallel. That is what common summing point it has been connected, and the output is given to the forward path gain of the second order system, which is omega n square divided by s into s plus 2 zeta omega n. Output is c of s, and then the feedback is taken, which is negative feedback is taken from the output. Okay, so that is what the negative feedback minus and r of s, which is positive. Okay, now we'll write the equation for g of s, where g of s equals kp plus kds multiplied by, okay, that is small d, kp plus kds multiplied by omega n square divided by s into s plus 2 zeta omega n. So which would be equal to kp plus kds into omega n square, kp plus kds into omega n square divided by s square plus 2 zeta omega ns, 2 zeta omega ns. Now we'll use this g of s to find out the transfer function c of s by r of s, where c of s by r of s is equal to kp plus kds multiplied by omega n square divided by s square plus 2 zeta omega ns, whole thing divided by 1 plus kp plus kds into omega n square divided by s square plus 2 zeta omega ns. So if I take the LCM and try to cancel this denominator terms, you will be getting c of s by r of s to be equal to kp plus kds into omega n square divided by s square plus 2 zeta omega ns added with kp omega n square plus kd omega n square s. Now you take 2 zeta omega ns and kd omega n square s are there. So we try to take s common in that two terms. So what do we get? Which is equal to kp plus kds into omega n square divided by s square plus s into, which is 2 zeta omega n plus kd omega n square into s plus kd omega n square into s added with kp omega n square. So this is the transfer function for the proportional differential controller. Now if you see here, kp is multiplied by omega n square. Normally we go with the denominator of the transfer function. We know we don't bother about the numerator. Always poles is what the concern is all about. So kp into omega n square, what we have, when kp increases, it multiplied by omega n square, that will also increase. But it's very important to see that 2 zeta omega n plus kd omega n square, where kd increases, omega n square increases, that term will increase, kd omega n square will increase Therefore, once that term will increase, this term 2 zeta omega n can be neglected. Okay, it will be neglected. Therefore, proportional differential controller can also be used for controlling zeta, because we know that zeta is critically damped or over damped or whatever the undamped condition that we see. So if zeta is controlled, then the response of the second order system can also be controlled. That would be happened if KD increases. If KD increases, then omega n square will also increase. In this summation part, you can see that 2 zeta omega n can be neglected if the term KD omega n square is increased. So therefore, this would be the benefit of the proportional differential controller. Let us now look into a proportional integral differential controller. Proportional integral differential controller. Let us now look into proportional integral differential controller. Okay. So let us write the block diagram for the proportional integral differential controller. So let us write the block diagram for the proportional integral differential controller. So E of t is the input. We have three blocks here now. One is proportional Kp, the another one is integral Ki into integration dt, and the third one is Kd into d by dt, Kd into d by dt, which is all connected to a single summing point. Okay, all connected to a single summing point, and n of t, which is plus plus and plus. So therefore, n of t equals Kp into E of t plus Ki into integration of E of t dt plus Kd into d by dt of E of t, which is n of s will be equal to Kp plus Kp into E of s plus Ki into E of s by s plus Kd into s into s into E of s, s into E of s. Okay. Now you take E of s common and try to write the transfer function n of s by E of s. You will be getting Kp plus Ki by s plus Kd into s. Okay. So this would be the transfer function gain which we connect in the second order control system block diagram, where the controller has been added to that. So therefore, the PID controller block diagram, let us write it. So we have a summing point, R of s is given to a summing point. Now you take with three different blocks. One block is with the gain Kp, the another block is with the gain Ki by s, the third block is with the gain Kds. All these three is given to a single summing point. All are plus. The output which is taken is n, means the output of this is given to the second order system, omega n square divided by s into s plus 2 zeta omega n, and the output is taken as C of s. Negative feedback system is connected now. Okay. So this is the negative feedback. R of s is positive and negative feedback. Now we write what is G of s equals. So let me write what is G of s equals. So G of s equals Kp plus Ki by s plus Kds multiplied by omega n square divided by s into s plus 2 zeta omega n. Now you take the LCM for the left part in the equation, where we get Kps or Skp plus Ki plus kds square multiplied by omega n square, whole thing multiplied by omega n square, divided by s gets multiplied with that s into s plus 2 zeta omega ns, so s square into s plus 2 zeta omega ns. So omega n, sorry, s is not multiplied inside, okay. So s plus 2 zeta omega n. Now we will apply this g of s into the transfer function c of s by r of s. So let us see what do we get, okay. So we will apply this to obtain the transfer function c of s by r of s. I will just directly write c of s by r of s, okay. I will directly write this where denominator and all gets cancelled. We know that g of s by 1 plus g of s equation. So I will just directly write c of s by r of s, which is equal to skp or kps plus ki plus kds square multiplied by omega n square divided by s square, which is s cube, okay, s cube plus which is s square into s plus 2 zeta omega n added with the whole term which is there in the numerator, kps plus ki plus kds square into omega n square into omega n square. Now you write complete equation in a normal way, kps plus ki plus kds square plus into omega n square divided by s cube, s square into s is s cube plus 2 zeta omega ns square plus kps into omega n square, okay, plus ki into omega n square plus kd omega n square into s square. Okay, now what we do, we take the term which is common between s square. So what do we get? So kps, so we'll write the numerator as it is, kps plus ki plus kd s square into omega n square divided by s cube plus, we take s square common, so you will get 2 zeta omega n plus kd omega n square multiplied by s square plus, so that is where we took the common for this, added with kp omega n square s plus ki omega n square. So this is the total transfer function for PIT controller, which is proportional integral differential controller, where you can see again one pole is been introduced in the denominator, therefore the stability will get reduced because of one pole introduction into the system, where the time constant ki into omega n square, where we have that. So due to that we will see that steady state error is eliminated, okay, will be eliminated in this particular PIT controller. You don't get steady state error, okay, and then you will see that the time constants like rise time and the the rise time gets reduced due to the kp, okay, due to kp, which is the proportional constant kp reduces the rise time. Similarly, we also see that the settling time is reduced due to kd, okay, the settling time is reduced due to the kd in PIT controllers. So settling time or the peak time also gets reduced in the PIT controllers. So as the peak time reduces, MP reduces. Once the peak time reduces, you see that the output reaches very fast, so that the settling time is also reduced. So all these times are interrelated, okay. If one time specification reduces, you see other times also reduces. So as S cube is there here, this system will introduce one pole, therefore the stability is very much, stability concern is not happened in PIT controller, okay. So I hope with all these different types of controllers that you people have watched in both the videos, I hope you are clear about proportional controller, differential controller, integral controller, proportional integral controller, proportional differential controller and proportional integral differential controller. Okay, thank you.